Welcome everybody. Today we have Géza Lévai, and he will answer the question, do similar potential shapes lead to similar physical results? And he will discuss this in the context of PT-symmetric potentials, as you can see. And I'm not sure what the sharks are about, but you will tell us later, Géza. Sure. So when you're ready, go ahead.
Okay, so PT symmetry. Hello, everybody. It's nice to be here, present a talk in this seminar series. So PT symmetry is now 25 years old or something. So there were many presentations, many conferences. So PT symmetry has been presented in various aspects. And I'm planning to talk about another type of approach, not like the ones which you usually follow when you talk about some result. Here, I will show you some interesting findings which are related to two specific potentials, which resemble each other, but which are still different. And there are interesting similarities and interesting similarities between them. So the shark and the dolphin here symbolizes that in the same environment, the animals or the species will look like more or less the same. So a shark and the dolphin, it's about the same size, they eat about the same thing, and so on. But it seems that not everything is the same for them. So I think the two potentials which I'm going to show you will be in a similar position. So they resemble each other, but they are not completely the same. Okay. So first, let me show you some philosophical thoughts about how do we think about quantum mechanical potentials. So as everybody knows, they represent the interaction of quantum mechanical particles, but they are not the only players in this. So for example, the position-dependent mass can also mimic somehow the environment of the particle, but anyway, the potential, quantum potential, is the important aspect of describing quantum mechanics. And its concept is deeply rooted in physics. It has a classical correspondence. So when we are talking about the quantum mechanical potential, we are talking almost at the same time on a similar potential on a classical level, and we understand how it works. It's easy to visualize. If you look at a potential curve, you can decide immediately that it's a weak or a strong, short range, long range, attractive, repulsive. A lot of things can be figured out from the looks of the potential. Sometimes it is an approximation of the real situation, sometimes it is more or less reality. So it's a good tool to handle quantum mechanics. And the solutions will carry all the physical information we need. Everything is fine as long as we are in the real domain of potentials. But if we go to the complex domain, we tend to lose the soil from beneath our feet. So anyway, potentials can be extended to the complex domain, and it has been done extensively in nuclear physics, for example. Complex potentials have been known for a long time. They are responsible for losing the flux. With the opposite sign, one can also account for the increasing flux. And if you combine the two, you reach PT symmetry, where the most important aspects of PT symmetry come around because of the fine balance of the emission. And so the two signs correspond to loss of flux and increasing of flux, and the balance of the two will give you PT symmetry. And here, as I mentioned, the problem is that if we are not too far away from the Hermitian situation, we more or less can follow what is happening. But if we go far away to the non-Hermitian region, then something strange will happen usually. Okay. So I talk about a little bit on symmetries because they are also important aspects. So PT symmetries, as we know, corresponds to simultaneous space and time reflection, and in the case of potentials, this formula is valid. So your potential will have a real component, which is an even function of x, and imaginary is an odd function of x. So this is again a delicate balance of emissive and absorptive regions. If you go to the mathematical interpretation, it corresponds to relaxing the hermiticity requirement, and it is a special case of pseudo-hermiticity, as we know. And it has unusual consequences. There are real eigenvalues, which was a surprise in the beginning, because when one was considering complex potentials, everything turned complex and hermiticity and orthogonality was lost. But here, there is something that, that reminds us of a Hermitian situation. So we have real eigenvalues, not every time, but quite frequently. And we can also have complex conjugate pairs, which corresponds to breakdown of PT symmetry. And it has a very interesting history. So it started as a mathematical curiosity of the IXU potential. And then now we are at optical experiments after 20 years. Okay. I also spent some time on praising exact methods in quantum mechanics, because they are a useful tool to understand new aspects of physics always. So numerical methods are there. You can use numerical methods, you can use approximations, but sometimes it is convenient to have in the background an exactly solvable system. So, okay. So if we go to PT-symmetric quantum mechanics, these exact solutions are again very important, because numerical methods cannot give you back all the delicate results of quantum mechanics, I think, in PT symmetry. Here you can go through the PT breaking point fully analytically. You can get all the information out exactly. Okay. There are also some interesting results that if we are not too far away from the Hermitian settings, so we have a moderate imaginary potential component, then the energy eigenvalues tend to stay real. So it is close to the Hermitian situation. And if we are too far away from the Hermitian situation, if we have too strong imaginary potential, then sometimes we find that the energies are again fully real, and they seem to be frozen in a real state. It is the case like in the IXQ potential. So there are some examples where these effects can be studied analytically. I present briefly the SCARF2 and the Rosen-Morse potentials, which have the same real potential component and different imaginary potential component. In the Rosen-Morse 2 case, the energies are always real. So there are no complex energy solutions. This can be proven analytically. It has.
What do you mean? Sorry, can I just ask a question? What do you mean by far away from the Hermitian situation? Not far away.
So, for example, in the IX cube case, you don't even have a real component. So it depends on from case to case what it means. But I will show you some examples that will become clear. So, okay, in the Rosen-Morse case, there is a finite non-vanishing imaginary potential component, and it is very different from what we have usually. Okay, so let me show you first the SCARF2 potential. This is the best and most favorite example for PT symmetric studies. It has a Stellar type real component and the odd potential component, and both potential components vanish asymptotically. The energy eigenvalues can be expressed in closed form, and the wave functions also. And there is an interesting quantity called quasi-parity, which can be put into the formulas as a sign of the parameter alpha. If you replace alpha with minus alpha, everything here remains the same. So the potential remains the same, but the wave functions will change. So the wave functions will have different structure for plus and minus values of Q, the quasi-parity. And this will also show up in the case of normalizability. So there will be two sets of eigenfunctions identified by the n principal quantum number, and both will start with 0 and build up. And if you look at the spectrum, this is the potential here, and this is the spectrum normalized to it. So if you start with 0 imaginary component, then you have 3 bound states in this case. As you move away from 0, increase non-hermiticity, then one by one new solutions will come in here, for example. Here, for example, and they merge at a certain critical point, and from that time on, they continue as complex conjugate pairs. Here I just indicating the real component. The imaginary component is increasing as you go away to the larger values of non-hermiticity. So the complex energy eigenvalues appear at the same location in each case. So for each n, each principal quantum number, the complexification of the energy eigenvalues is set in at the same point. There are other examples where it is a continuous process, but in most exactly solvable cases, this is the situation. I call it the sudden mechanism of PT-symmetric breaking. Sudden because it is related to a point in the parameter space. So let's see now the other case, other example, the Rosen-Morse potential. The real potential component is the same. The imaginary one is different. It is non-vanishing asymptotically. Tangent hyperbole goes to constant values in the two directions. Okay, and here the energy eigenvalues can again be expressed in a closed form. They are real and they are limited. This parameter S here limits the number of bounds of normalizable states. But there are interesting differences with respect to the SCARF2. There is no quasi-parity. There is no doubling of the energy levels. So there are no complex energy eigenvalues, no spontaneous breakdown of PT symmetry. But what happens then if you increase non-hermiticity? In the case of the SCARF2, we realize that the complex energy eigenvalues appear if the imaginary potential component exceeds a certain limit. Here, nothing like that happens. Rather, what happens is that the energy eigenvalues just fly away. They increase infinitely. So they remain real all the time, but increase. And this is somewhat similar to what we experience in the IX3 potential, for example, and some others in the numerical domain. Okay, now, so here we have this potential, which is quite peculiar. It has the Pursteller Hall as the real component, and it has the tangent hyperbolic as the imaginary potential component. So my idea was that why not devise a solvable potential which resembles this in many respects. It has a finite asymptotic value in the imaginary domain, and it has a finite depth, and it is finite in every sense. And still, it should be possible to get out the energy eigenvalues and wave functions. So I checked the so-called PT-symmetric square well potential. The PT-symmetric square well potential is starts essentially with the square well potential, which is here, which is minus V0 within certain limits. And outside it, it is not zero, rather it has a finite constant imaginary potential component. So it mimics the SCARF2 potential. It can be considered to be a semi-analytic solvable model of the PT-symmetric Rosen-Morse potential. So it is a kind of experimental theoretical physics now what I'm doing. Okay, so let's see how to handle this problem, this potential. all the solutions can be written in the three domains in terms of exponential functions. So you have to put together your solutions from three pieces and match the wave functions and the derivatives at the boundaries. The boundary is plus and minus a. It's a finite domain. So these conditions will indirectly determine the discrete energy eigenvalues. Okay, let's see how we can proceed. So consider first real energy eigenvalues. In that case, the P plus and P minus quantities, let me remind you that they are these quantities, they will be used widely in the following. So these quantities appear in all these formulas, and the PT even and PT odd solutions can be constructed. And in that case, the condition for having a PT even solution means these three or four equations. This means that alpha and beta, which appear here, should be real. And out of the four f functions, they two should be pairwise correlated in a way. The same is valid for odd solutions. Okay. And if you want to get out all those solutions which are normalizable, which decay asymptotically, then you have to look at the what is here in the exponent. What is the real content of the exponent? That is the imaginary component of the P minus and P plus quantities. So it will be an important layer. And then if you want to get rid of all the other solutions, the exploding solutions, then you have to set some of your f functions to 0. And this will guarantee that you will have a continuous solution which is PT-symmetric and decays asymptotically. Okay, here some care should be taken, because if you are looking at these exponential factors, then as I said, what will determine the asymptotic behavior will be the sign of P plus and minus I. That is the imaginary component of the P plus and minus functions or quantities. Okay. Now, how can we find the normalizable solutions for this P? As I said, for this we have to select those coefficients which are together with the asymptotically exploding solutions. You set them to 0, and from that you will get a set of two algebraic equations. You can solve it for alpha and beta. Let me remind you that alpha and beta are two components of the wave function inside the box. And then if you want to solve it, of course, it's a homogeneous algebraic equation, then the determinant should be 0. You get a nice equation. This mu and psi are p and k normalized with the length the variable a. And if you plot it, you will have this nice wavy structure. And the zeros of this curve will supply you with the energy eigenvalues. So here I plotted this function here from the bottom of the potential well up to 0 energy. And the black line or red line, which is here, represents the real solution, the real case. That means Hermitian case. And then gradually the green line is a little bit Hermitian, the yellow line is more Hermitian, and the blue one here is even more non-Hermitian. And as we see, if we switch on non-hermiticity, the energy eigenvalues will shift to the higher values, as we saw it in the case of the scarf 2 also. Okay, so then if we determine the solutions of this algebraic equation, we have alpha and beta. We then can determine the ratio from the normalization, and we can put everything into the formulas, and we have all the wave functions ready. Okay. So now what happens for positive energies? That means if we are above the 0 energy level. So here, if we stay with the energy below the threshold, then the moment in the momentum space, we are going to have this distribution of this P and K momentum-like variables. If we cross this limit, we go to positive energy, then more or less everything remains the same, except for that the P quantity, which is the square root of energy, that will be real, while in the other case they were positive. Okay, so it turns out that these states, these solutions behave just like the bound states used to behave in the negative energy region. So it seems that they survive. These solutions, these normalizable solutions survive as we go with energy to positive values. And it is exactly the same what we experienced in the Rosen-Morse case. As you remember, when we increase non-hermiticity, then the positive energies just exploded and went to infinity gradually. Okay, so we can just do the same trick. We can extend the energy from 0 to positive values, and the pattern of this function, which determines the energy eigenvalues, is pretty much the same as in the negative energy range. So we have all this situation very similar in the positive energy domain as in the negative energy domain. Okay, let's see what about complex energies. Are there complex energy solutions? We cannot be sure, so we have to search for them. The situation here is more complicated. If you allow the energy to be imaginary, then in the momentum space, these plots will behave in a more complicated way. So P plus and P minus will not be compressed conjugate pairs anymore, but new relations arise. So there are a couple of new relations which will replace this one, and the PT operation, when you act on the solution, will give you back the expected result that the PT transformation will flip between the complex energy solutions. So it is normal. This is what we expect. So definite PT parity is lost, and here comes the question. Are there normalizable complex energy levels? So this means that you have to extend your search for zeros of this determinant, which determines your energy eigenvalues, to the whole complex domain. So the question is whether there are any zeros of this function on outside the real axis. And this paper, which I was citing, explains it in detail. Here I skip the details. So I put this figure here to remind you that if you like beer and sausages, then try to avoid seeing how they are prepared. So I think this applies to my results of proving that there are no complex energy solutions of this problem. But the paper contains everything. So if you assume that your energy has an imaginary component, then you will run into a contradiction. So you can exclude the possibility of having complex energy solutions there, which is completely in line with the result of the scarf-2 potential. There are also no complex energy solutions there. And that is proven exactly in terms of quantum mechanical methods. So let us check the transmission and reflection coefficients. This is a standard thing in quantum mechanics, PT-symmetric quantum mechanics. It has characteristic features there. So these quantities can be determined exactly in closed form. If for a particle coming in from the right, these are the two coefficients, the transmission and reflection coefficient. They are nicely expressed in terms of the physical variables. And if you do the same for the particles coming from the left, you will find that they are not related in the same way as in the Hermitian setting. So in the case of the transmission coefficient, you essentially have a factor here in front of the two transmission coefficients. So it's a relatively simple matter. It is actually a phase, more or less, because for real energy eigenvalues, these two quantities are complex conjugates, so it will essentially give you a phase. But the situation is more complicated for the reflection coefficient. Here you have a more complicated relation between the right and left variable. Okay, so as I said, we proved that this PT-symmetric square well potential doesn't have complex energy solutions, and it is very similar to what we found for the scarf, for the Rosen-Morse 2 potential. And here I present you another consistency check of the results. So we studied another potential, which is known in PT-symmetric quantum mechanics, which is the real Dirac delta and the imaginary sine function. And it is known to have a single bound state and solutions of this kind, where kappa is a complex number. And you can get this potential in both cases. So if you go to the Rosen-Morse case, you have to rescale the coordinate and go with the scale to infinity. In that case, the cosine hyperbolic inverse square cosine hyperbolic function will give you the Dirac delta, and the sine function will give you the tangent hyperbolic, or vice versa. So the tangent hyperbolic will go to the sine function. The 1 over cosine hyperbolic square will go to the Dirac delta. So it is an exact limit. In the case of the finite square well potential, you can also play around with a limit situation. So if your A, which determines the size of the hole, if you go with it to 0, you will have an infinitely deep and infinitely narrow potential, real potential, that is exactly the Dirac delta. While in the case of the tangent hyperbolic, in the case of the imaginary component, it simply goes into the sine function. So in both cases, you can exactly reach as a limit this function, this potential. And it turns out that if you go through this limit process in both cases, you nicely get back all these results which are here. So it is a kind of consistency check for the problem. Okay, but there is some interesting difference in the behavior of normalizable states. So if you look at the normalizable states, as I mentioned, the energy is real and increases rapidly if you increase non-hermiticity. And these states can be related to the transmission resonances in the Hermitian limit. In the case of the Rosen-Morse potential in the Hermitian limit, you have this Pursteller potential hole, the real component of this Rosen-Morse potential. This potential is known to have a very special feature, that it can have a complete transmission for all energies at specific depths. So at all energies, it will be transparent. And this comes at specific depths when this S times S plus 1 is the parameter of the coefficient of the real potential component. If S is a positive integer, then you have this situation. And this can be explained very nicely in terms of supersymmetric quantum mechanics, because this potential is the partner, supersymmetric partner of the free motion. So the free motion is transparent, and transparency is inherited by this potential at specific potential depths. Okay, what about the finite square well potential? Here we again have also perfect transition in the real case for all depths, but for specific energies. So the energy is determined by this relation. So in this case, the two problems have something different. Of course, the shape is different. So this is the consequence of the different shape. So the global shape is more or less the same, but the precise shape is not exactly the same. So in the case of the finite square well potential, this special feature can be explained by the fact that the waves fit into the box if they are at certain parameters. So the situation is again similar to the shark and the dolphin. They look more or less the same if you look at them from a distance, but there are marked differences. So for example, the tail fin of the shark is oriented vertically. In the case of the dolphin, it is horizontal. So it is a difference like this here in the case of these two potentials. So this is just an example that there are differences also. Okay, so I think I more or less conclude my talk. It was not a very long one. So as I said, the Rosen-Morse potential had a real spectrum with energies which explode or fly away as non-hermiticity is increased. And one suspects that this may be due to the non-vanishing potential term, which is finite in the asymptotic limit. So we constructed a model of this potential, the PT-symmetric square wave potential, which is semi-analytically solvable. It has similar shapes, similar physics, despite the different mathematics. It is not exactly solvable, but you have to solve you have to find the roots of a transcendental equation, which is again something feasible, but it is not completely exact. So it turned out that the main features of this potential mimic the properties of the Rosen-Morse potential. So the answer to the question which I raised in the title, that are the two potentials similar, or can the physical results are similar or not? Partly they are similar, partly they are not, but the cross features are, the most important features are the same. So as I said, levels with energy, real energy, stay normalizable if you go to positive energy, and climb rapidly if you increase non-hermiticity. This is in line in the case of the two potentials. We also proved exactly that there are no normalizable complex energy solutions in either potential. So this seems to fit into the picture that if you have this infinite asymptotic finite imaginary potential component, then you can expect this kind of behavior. And finally, there was this simple consistency check that these two potentials have a common limit asymptotically, the Dirac delta plus imaginary step potential, and it turned out that calculations match. So in the end, everything came out right. Okay, thank you.
Thank you very much. Questions, comments? Carl.
Yeah, can I just ask, when you say there are no normalizable solutions, well, you mean normalizable on the real axis, or
normalizable is that the envelope goes to zero.
Okay, on the real axis.
On the real axis, yes.
On the real axis, okay. I mean, there could be no normalizable solutions on the real axis, but solutions that do vanish exponentially fast in some direction in the complex plane, right? I mean, there's no a priori reason why you need to restrict yourself to the real axis. Is that right?
This is the first step. So I was trying to mimic this Rosen-Morse potential, and that is defined on the real axis, real x-axis. Of course, it can be shifted to a parallel line very easily. It stays analytical, calculable. But as a first step, I was staying on the safe area, the real axis. It is possible that that if you go to complex directions, then there will be also normalizable solutions.
Okay. Could you go back to where you're talking about the transmission and reflection coefficients for this square well potential, please? Okay. Okay, so I was I mean, it's a long time since I've thought about these things, but I always thought that there was a general theorem that T left was equal to T right.
Yes, in the case of of real energies, it is just a phase.
Yeah, but even so, and there should be a pseudo unitarity relation between these things. You know, the ordinary unitarity is T plus R equals 1, but normally in PT symmetry instead, you've got something like T plus the square root of R left, R right equals 1. I don't know if you checked that.
It can happen, so I can check it. So I check it, but
doesn't look obvious.
it doesn't look obvious. Of course, one can check, so it is possible. But I have to add that this Rosen-Morse 2 potential is a very strange animal also in the case of the Hermitian setting, because asymptotically the potential limits are different. So the momentum will be different in one direction and the other. So it's real. So it's a strange animal also in Hermitian situations.
Okay.
Géza, it's Uwe asking a question concerning the normalizability of this in the sector of broken PT symmetry, but with regard to the PT inner product. In this case, you are combining actually you have the same real energy or real component energy, and the imaginary parts are compensating each other.
Yes.
Did you check this? Does this work or?
Sorry, I didn't catch it. So I found that there could be complex energy eigenvalues at all.
Yeah, sure. No, but when you have complex conjugate pairs of eigenvalues, and you are choosing the PT inner product, then you are combining. You have this. How to say this? They are with regard to the PT inner product. They are mixing this, actually the positive imaginary part and the negative imaginary part, and they might compensate each other. There have been similar effects in the Green's function that Philip was using. There you have also such an effect. I'm wondering whether you can show this explicitly for your solutions as well. Would be very interesting.
Here, if you use these solutions, for example, for a PT even solution, then you do the integration in 3 different domains.
Yeah, okay.
Everything comes out easily. Okay, so it seems to be a finite.
Yeah, it should be normalizable with regard to the PT inner product. And this is the same thing that Hugh was mentioning. You have this invariance with regard to pseudo structures. It means pseudo-unitarity and pseudo-hermeticity in this sense that you have to use the PT inner product to get these invariants and additional symmetries, even in the sector of broken PT symmetry. You have just a tricky, very fine-tuned combination of these 2 components of the wave function with positive imaginary part of the energy and negative imaginary, and they are compensating in a very tricky way. So it might yield some additional information also on your transmission coefficients and so on.
No, I understand. Okay. I will check how it comes out in this situation.
Thank you. Very nice talk. Okay, thank you.
More questions, comments?
I ask a question.
Milos.
Those 2 potentials have this property of exactly solvable things in the most straightforward way, which was used by Géza, represented on the map, where this coincidence of complexifying points was a characteristic feature in contrast to gradual complexifications in not solvable models. So my question is something in between?
Yeah, so you are asking about the mechanism of PT symmetry breaking, is it?
Yeah.
Yeah, so in most of these analytically solvable cases, this PT breaking is occurring at a certain parameter point. So it is not a continuous process, most of them, but there are exceptions. So seems that when your spectrum can be calculated in a closed form, you more or less get this result. But if you have to involve also some transcendental root finding and things like that, this is where this other scenario comes in, when this gives enough room to introduce this continuous breakdown of PT symmetry. There are examples for that. So if you start with a zero imaginary potential component, then one by one, these pairs appear. Not at the same time. There are examples for this also.
Thank you.
My impression is, my experience with these is that if you have a more nice analytical result, then it tends to be this sudden mechanism. If you have a less strict situation, I mean, your solution contains some root finding elements in numerical way, then there is a chance that the PT symmetry breaking will be a gradual mechanism.
Thank you.
Frida has a question.
I think in 2001 you published with Miloslav a paper on this imaginary step potential, or
Yes.
and I had the feeling there you didn't have an analytic solution for the bound state. Now, when you combine it with a delta potential, it seems that you can give an analytic solution to it. So what's the difference then?
That potential was different because that was a finite hole. So it was the whole problem was confined in a box, and inside was an imaginary potential component. So there was an odd function of some, I think it was a step function also, but it was inside, not outside. So that was a confined box. So it's a different story. This is, it turned inside out in a way.
More comments, questions? If not, then let's, yeah? No. Then let's thank Géza again. Thank you.
Thank you.